Welcome to AI Paper Podcasts. We dive into the latest AI research papers, breaking them down for you. Today, we're looking at how large language models keep learning new tricks without completely forgetting the old ones.
That's right. It's all about continual pre-training, or CPT. This paper introduces a really neat scaling law. It helps predict how a model's performance changes during CPT.
And it considers two key things, right? The difference between the old and new training data, and also how you adjust the learning rate over time.
Exactly. One of the coolest insights, I think, is that models which haven't been trained to their absolute maximum potential on their original data actually seem to adapt better later on.
That's pretty interesting. But there's a catch, isn't there?
There is. The law predicts that if you specialize too much for too long, the model's general abilities will degrade. It's a trade-off.
So this law helps quantify that. Okay, so for all you AI researchers and ML engineers out there tuning your models, this paper could be really valuable for optimizing those continual learning strategies.
Definitely. The paper's titled Learning Dynamics in Continual Pre-Training for Large Language Models. It's from the proceedings of the 41st International Conference on Machine Learning, ICML 2025.
And the authors are Xingjun Wang, Hao Tishu, Lu Wang, Linjing Li, and Daniel Dajin Zhang.
Yeah, and they've done some great work here looking at validation losses on both the original sort of general data and the new domain-specific data to track how things change.
So our mission today on AI Paper Podcast is to unpack this research. We want to pull out the most practical findings, especially around this CPT scaling law, and really talk about what it means for your work.
Right. How can you use this to understand what's happening during CPT and maybe make better choices about, learning rates, how long to train, that kind of thing?
The paper really sets out to answer two main questions, doesn't it?
It does. First, can we find a single, accurate law that captures as many variables as possible that affect CPT performance? Things like the data, the learning rate schedule, the starting model.
Okay, a comprehensive model. And the second question.
Can we track the performance throughout the CPT process, not just look at the final result, understand the journey, not just the destination?
Got it. All right, let's dig into the core problem. Continual pre-training. We have these incredibly powerful foundation models.
Huge models trained on vast amounts of data.
But then we want them to be good at specific things, coding, maybe medical diagnosis, finance.
Right, specialized domains, and CPT is way more efficient than retraining from scratch every time.
But the big headache is catastrophic forgetting. You make it better at finance, and suddenly it's like worse at general conversation or other tasks it used to know.
Exactly. It's this constant balancing act. People have looked at scaling laws before and things like replay buffers, mixing in old data. But this paper really tries to quantify the dynamics. How does the loss, which measures error, actually evolve over the training steps for both the general and the specific domains?
So how do they approach this? What was their methodology?
Well, as we mentioned, they used validation laws. They tracked how well the model performed on data it hadn't seen during training, both from the initial pre-training set.
Like FineWeb, a general web data set.
Exactly. And also from the continual pre-training set, the new domain. They use Knowledge Pile as an example there, which is more specialized.
Okay. And they also played around with the learning rate schedules, right?
Yeah.
The speed of learning.
Yeah. They looked at keeping it constant, which is simple, but also more complex schedules like warm-up stable decay or WSD.
WSD.
Yeah.
That's where you ramp it up, hold it, then slowly bring it down.
Precisely. That's a common one. So they wanted to see how that schedule impacted the whole process.
Okay, now here's a really core idea from the paper. The CPT Lost Curve itself. They argue it's not just one simple curve.
Right. It's better understood as a kind of transfer curve. Think of it like a bridge connecting two other sort of hidden performance curves.
Hidden curves, what do you mean?
Okay, imagine one curve representing what would happen if you just kept training the original model on the original data indefinitely. That's one baseline.
Right, the hidden PT curve on DPT, as they call it.
Exactly. Now imagine another curve. What if you trained a model from scratch only using the new specialized domain data?
Okay, the hidden PT curve on DPP.
Yeah. The actual CPT curve you observe is basically the model's performance transitioning between these two underlying possibilities. It starts near the first curve and moves towards the second.
I see. And the gap between the actual CPT curve and that first hidden curve, the one for staying on the original data, what do they call that?
That's the key bit, the distribution shift.
Yeah.
It essentially measures how much the performance deviates simply because the data has changed. How different is the new stuff from the old?
Got it. So that shift quantifies the impact of the data change itself.
Exactly. And this leads directly to their main contribution, the CPC Scaling Law. It elegantly combines two pieces.
Okay, what's the first piece?
The first piece builds on existing work about how loss changes during training when you use learning rate, annealing that gradual reduction.
Right.
It involves terms related to the total learning done, kind of like the area under the learning rate curve. They call one part the forward area, S1, and another the annealing area, S2, which captures the effect of the changes in the learning rate.
Okay, so that handles the learning rate schedule's impact. What's the second piece?
The second piece is modeling that distribution shift, ALT.
How did they figure that out?
Through experiments. They tried starting CPT at different points in the original pre-training, using a constant learning rate just to isolate the shift, and they found something quite surprising.
What was that?
The magnitude of this shift seemed to be independent of when they started the transfer. It didn't really matter how far along the original pre-training was.
Huh. Interesting. So it's more about the inherent difference between the data sets.
It seems so. They found this shift was best described by a power law function, something like b times 1 minus e times t plus 1 to the power of minus beta.
Okay, some constants b, e, and beta defining the shape based on the data sets.
Exactly. And then, to make it work with any learning rate schedule, not just constant ones, they adapted it using that forward area concept, again, the cumulative learning during CPT, CPT1.
So it's not just time, but the effective learning that drives this shift.
Precisely. So the final integrated law looks like this.
Yep.
LT equals LT plus LT.
Is the loss at time t.
Yep. LT is the part that accounts for the learning rate annealing effects from both the original pre-training and the CPT phase. It even has slightly different parameters for each phase because the data sets are different.
Okay, and LT is that distribution shift term, modeled by the power law, adapted for the cumulative learning.
You got it. That's the core equation.
All right, so we have this fancy new law. What does it actually tell us? What are the big implications for people training these models?
Well, several really practical things fall out of this. One is about loss potential.
Loss potential.
Yeah.
It says exactly.
It's basically how much further the original pre-trained model could have improved if training on its original data had continued. So a model with higher loss potential wasn't trained quite to its absolute limit.
Okay.
And the finding is models with higher loss potential, the ones that weren't fully annealed or trained to the max, actually adapt better during CPT. They tend to reach a lower final loss on the new domain data.
Whoa, okay. That feels a bit backwards intuitively. You'd think a better initial model would be better overall.
Right. But it suggests that maybe leaving some learning capacity, some potential, makes the model more flexible for adapting later. Releasing open source models that aren't squeezed for every last drop of performance might actually be better for downstream users doing CPT.
Huh. That's a really interesting strategic point for model providers. Did they test this?
Yeah, they did experiments, including ones where they rewarmed up the learning rate briefly during CPT, which supports this idea.
Okay, what else?
Another key prediction, and maybe a slightly sobering one, is about performance on the general domain, the original tasks. The law predicts that if you run CPT for long enough, performance on that general domain will inevitably degrade significantly, especially if the distribution shift is large, meaning the new data is very different.
So that catastrophic forgetting isn't just avoidable noise, it's kind of baked into the process if you push specialization too far.
According to this model, yes. It really highlights that CPT duration is a critical choice. You can't just train forever on the new domain without consequences for generality.
Makes sense. But the upside is prediction, right?
Absolutely. This is maybe the most powerful application. The CPT Scaling Law can potentially be used to predict the optimal hyperparameters for your specific goals.
Like what?
Things like, how much loss potential should your starting model ideally have? What's the best peak learning rate to use during CPT? What's the right replay ratio? How much original data should you mix in?
So you could use the law to simulate different scenarios and pick the settings that give you the best balance between, say, improving on the new task and not losing too much general knowledge.
Exactly. Instead of just trial and error, which is super expensive with these models, you could make much more informed decisions up front. It's about predicting that trade-off.
That sounds incredibly useful.
Yeah.
What else influences the outcome?
Well, the distance between the data sets, as we discussed, they showed this experimentally, using a very different data set for CPT, like pile of law compared to knowledge pile, resulted in a much larger distribution shift and thus more degradation on the general domain.
Okay, so the more different the new task, the bigger the hit on general skills.
Seems logical, and the law quantifies it. And related to that is the replay ratio.
Mixing in the old data.
Yep. Using some original pre-training data during CPT definitely helps mitigate that distribution shift. Higher replay ratios lead to smaller shifts.
And the cool thing is, the law doesn't just predict the final loss for a given replay ratio, right?
Right. It predicts the entire loss curve throughout CPT for different replay ratios. So you can see how replay affects the dynamics over time.
That's a much richer picture.
Right.
What about the learning rate during CPT?
Another trade-off there. A higher peak learning rate can speed up learning on the new domain, get you good performance faster.
What?
But it might also accelerate the forgetting on the general domain. Again, the law can help predict this balance based on the peak LR you choose.
Okay. Lots of knobs to tune, but the law gives us a map.
Sort of, yeah. And there's another subtle point about the general domain loss. They found something called a critical point in the initial pre-training.
It's a critical point.
Yeah. If you start CPT before the model reaches this point in its initial training, something interesting can happen. The general domain loss might go up at first.
Which you'd expect.
But with enough CPT steps, it could potentially dip back down, maybe even below where it started. They called the number of steps needed for the turning length.
Wow. So CPT could, under the right conditions early on, actually end up improving general performance in the long run.
It's a possibility suggested by the model, yeah. It depends heavily on the starting model state and the size of that distribution shift. It's not guaranteed, but it's a fascinating dynamic.
Definitely. So how do we actually use this to balance things?
They propose a framework using normalized balance coefficients. Basically, you decide how much you care about improvement on the new domain versus limiting the loss on the old domain. And you can use these coefficients to guide the optimization of the CPT hyperparameters towards your specific target balance.
That makes it very goal-oriented.
It does, and they even thought about out-of-domain validation.
OD. So testing on data that's related to neither the original nor the new training data?
Exactly. Stuff the model has never explicitly trained on in either phase. They suggest, as an approximation, that the loss on an O dataset can be modeled as a linear combination of the losses on the original DPT and new DTP validation sets.
Huh. So if you can predict the DPT and DTP losses using the main scaling law,
you might be able to predict and even optimize for O performance too by finding the right coefficients for that linear combination. It's an interesting extension.
very clever. Now, what about applying this in the real world? Often we get an open source model and we have no idea how exactly it was trained initially.
Right. The original dataset, training steps, its loss potential, it's often a black box.
So can we still use this law?
They propose ways to handle this. You can use a proxy general domain dataset, like a chunk of common crawl, to stand in for the unknown original data.
Okay.
Then you fit the unknown parameters of the scaling law, things like the initial loss potential, or annealing parameters using the performance you observe on your proxy dataset and the new CPT dataset.
So you infer the missing pieces.
Yeah, and you usually assume the original model was trained with a near zero final learning rate, which is common for released models. They showed this worked reasonably well in experiments with models like LMMA 3.21b and Red Pajama.
That's great. It makes the whole framework much more practical if you don't need the full training history.
Definitely increases its usability. Now, they do mention limitations. They discuss some alternative ways to mathematically formulate the annealing part, but stuck with this one for simplicity and effectiveness. And importantly, while the law holds up well in their experiments across different models and settings,
It doesn't have a rigorous theoretical proof yet.
exactly. Proving things about the dynamics of these incredibly complex LLM training processes is, well, notoriously difficult. So it's empirically grounded, but the deep theory is still developing.
Understood. Okay, let's try to synthesize this. What are the absolute key takeaways for the technical folks listening?
I think the main takeaway is this. We now have a quantitative framework, this CPT Scaling Law, that helps understand and, crucially, predict the learning dynamics during continual pre-training.
It's not just a black box anymore.
Right. By integrating distribution shift and learning rate annealing, it gives you a powerful tool. You can use it to think more systematically about optimizing hyperparameters, loss potential of the start model, peak LR, replay ratio, training duration to hit specific performance goals for both your new domain and the general capabilities.
And those insights about loss potential, maybe not training the initial model to death, and the inevitability of general degradation with long CPT are really important practical considerations.
Sure, those stand out.
Were there any findings that particularly surprised you, like real aha moments?
I think the independence of the distribution shift magnitude from the specific transfer point in the pre-training was quite striking. It really isolates the dataset difference as a key factor.
Yeah, that was neat.
And also the clear prediction of eventual general domain decline with prolonged CPT, especially with large shifts. It formalizes something we might intuitively suspect, but seeing it laid out in the scaling law really highlights this fundamental challenge in continual learning.
And the idea of predicting ode performance, even just as an approximation, that opens up some interesting possibilities.
Definitely. It suggests we might be able to aim for broader generalization during CPT.
So bottom line, why should you, our listener, care about this research?
Well, if you're an AI researcher, this paper provides a solid empirical foundation and a framework for digging deeper into the theory of continual learning, which is still a very active area.
And if you're an ML engineer?
If you're actually building or adapting these models, the CPT Scaling Law is a practical tool. It offers a way to move beyond just guessing hyperparameters for CPT. It enables more informed tuning, potentially saving compute time, and leading to models that better meet the specific needs of an application, balancing specialization and generality.
It gives you more control over that adaptation process.
Precisely.
Okay, let's end with a thought provoker for everyone listening. Considering this scaling law predicts an almost inevitable decline in general performance with extensive CPT, what kind of new strategies could we dream up? Could we develop ways to actively mitigate this forgetting beyond simple replay, maybe dynamically adjusting the replay ratio based on predicted loss changes? Or using adaptive learning rate schedules that respond to how the general versus specific losses are evolving according to the law?
That's a great question. Could we design CPT processes that are actively trying to stay on a desired trade-off curve, using the scaling law's predictions as a guide in real time?
Maybe some kind of regularization specifically targeted at the distribution shift component.
Yeah, lots of possibilities there. It points towards more sophisticated CPT algorithms in the future. We definitely encourage you to read the original paper, check out the details, the graphs, the math. Think about how these ideas connect to the systems you're working on.
And share your thoughts. Discuss it with colleagues. Contribute to the conversation in the AI community.
Absolutely.
Well, that wraps up our look at the learning dynamics of continual pre-training on this AI paper podcast session. Thanks for joining us.
We hope you found it useful.
Stay tuned for our next episode, where we'll tackle another exciting piece of AI research.